Hello, so today I'll be presenting this paper, SemGrasp, Semantic Grasp Generation via Language-Aligned Discretization. So what they do mainly is, given they have an MLLM, a multimodal large language model, and given an object, the user can give some instruction on how to hold that object, and then the MLLM outputs a grasp token on how that aligns with how how the object should be held, and it aligns with the user's prompt on asking how the object should have been held. So the grasp token can then be used to generate the manual hand pose. Uh, this approach inspired by human grasp planning. They divide the grasp into three interrelated components: orientation, influenced by the intent and the object's function; manner, specifying the grasp taxonomy required for interaction; refinement, detailing the hand pose adjustments necessary for physical plausibility. The contributions are as follows. They propose SemGrasp, an innovative grasp generation method integrating semantic information. They introduce a novel grasp discrete representation, efficiently and effectively expressing grasp posture and supporting the task of grasp description through language alignment. They compile CAT grasp dataset, the first dataset of semantic grasps that encompass low-level, high-level, and conversational annotations. So before we go into the architecture part, let's review VQVAE a bit, because the core architecture here is dependent on hierarchical VQVAEs. So let's say for VQVAE, let's say we have an image and we have an encoder, and the image passes through the encoder and we have the features. And then what we have here is a codebook vector. Codebook, which is a set of vectors that are initialized randomly at the start, but as training progresses, these are optimized. And there is the decoder part, but the way it happens is we take, let's say, along this dimension here, we take the values of a particular pixel across all channels in the feature, generated feature from the encoder. And for that particular vector, we compare against every vector in the codebook, and we check the L2 norm, and whichever is closest in terms of L2 norm with the codebook vector here, we take that codebook vector and assign it in that particular space. So E7 here would imply that for this vector over here, 7th codebook vector was the closest one, and E2 for the next one, and so on. And once we have this full feature space, we feed it to the decoder, and the decoder is supposed to reconstruct the image. So for losses, there are three components. There is first the reconstruction loss and the codebook loss. So codebook loss is used to train the codebook, this codebook part, which is the encoder's output minus the codebook vector. And there is a stop gradient on in the encoder part, because they don't want to. Stop gradient does what it does is it attaches the gradient and sets the gradient to identity. Sets the stop. So they do this so that the encoder part is not updated. The encoder part is not updated because of this particular loss term. And then comes the commitment loss term, which this is also, the expression is same, except that the stop gradient is on the codebook vector instead. And in this one, this is done so that the codebook vector is not updated with this. The encoder is, however, updated with this. And the purpose of this part is, as the authors say, so that the encoder output doesn't get too large. Yeah. And the encoder commits to a particular vector for, yeah, and the encoder commits to a particular vector in terms of that nearest neighbor selection. And the overview. The initial phase involves the tokenization of the grasp into 3 interrelated tokens by training the VQVAE. After the tokenizer is trained, the VQVAE is frozen, enabling the projection of tokens from the codebook onto grasp configurations. So once in this architecture here, we have 3 codebooks for each orientation, manner, and refinement. And once a codebook vector is selected, they can be fed into the VQVAE decoder, and that VQVAE decoder then generates a hand grasp. And here's the overview. First, the object point cloud is fed into the point bird, which outputs point cloud features, which is then fed to this, which is then fed to the linear projection here, which is then fed to the linear projection, and the linearly projected part is there, and we have language features coming out of the tokenizer and embedding, which come from the user provided prompt. Here in this example, it's please grasp the controller to play games. And together, the point cloud feature, the projected point cloud feature, and the language features are then fed into the MLLM, which then outputs the sentence along with 3 tokens, O, M, and R. O, M, and R stands for orientation, manner, and refinement, respectively. And these orientation, manner, and refinement tokens can then be fed into the hierarchical VQVAE decoder, as we saw earlier, and that is enough to generate the nano grasp for the object. So here are the notations for the grasp. Now we'll discuss the grasp, how grasp is discretized. Grasp is defined as G, which equals T, theta, and beta. T represents the homogeneous transformation matrix. Theta represents the hand pose parameter. Beta represents the hand shape parameter. And then Mano takes in these 3 quantities, and it outputs hand vertices of dimension 77 and 778 by 3. And the grasp G is discretized into O, M, and R, representing orientation, manner, and refinement tokens, respectively. A hierarchical VQVAE is employed, so they use not just a plain VQVAE, they use the hierarchical VQVAE, which we'll see how it looks like, which encompasses trainable codebooks BI, encoder EI, and decoders TI, and where I is equals to 1 to 3. So there are 3 hierarchies here, each denoted as 1 to 3. And for each of the hierarchy, we have separate codebooks, separate encoder, and separate decoder. Here is how the overall architecture looks like. The encoders progressively map the hand's representation into the latent space, capturing grasp information from low to high levels. This structured approach enables the simulation of the grasping process through conditional probabilities. So at first, we get during training, we have the hand features from point bird and the object feature from point word as well. And during training, the hand features are fed to the encoder along with the object feature, and out comes a vector, a codebook vector is selected from this, and that in turn is fed to the next encoder, and this output is fed to the last decoder part. Finally, the first decoder takes as an input the output of the last encoder and the object point cloud feature, and it outputs a codebook vector which can be used to get the orientation token. And the subsequent decoder takes in as input the previous decoder's output and the second encoder's input, and the object feature as input, and outputs the manner, and the manner token can be obtained from this output of the second decoder. And similarly, from D3, we get the refinement token. And now we see how those T, theta, and beta can be obtained from OMR tokens. So T is encapsulated by this expression here. O represents the orientation token, and the object vertices, object features, and D1 outputs the homogeneous matrix. Theta and beta is outputted by the second decoder, which takes in additionally the manner token, and changes in, for refinement purposes, changes in T, theta, and beta is outputted from the last decoder, which additionally takes in the manner token as input. And finally, once all these quantities are there, the changes and the predicted T, theta, and beta, the grasps can now be generated using Mano. For each in the architecture, for each input vector Z, the encoder E maps it to the latent space using a mapping network N, and finds the nearest codebook entry B, where Z is 1 through K. This would be the Z represents the number of codebook here. And the decoder D then it reconstructs the original vector Z with mapping network N. This is basically explaining how the VQVA architecture works in general. The encoder's output is matched to a nearest neighbor codebook vector, and that codebook vector is fed into the decoder to get the final output reconstructed out. And then for losses, we have the reconstruction loss, and then the embedding loss and commitment loss that we saw earlier for VQVA. It's the same one here. Now for the grasp-aware language model. So they use the Vicuna checkpoint and use LoRa to fine-tune the grasp-aware MLLM, and then they freeze it. And then so what it takes as an input is object features, object point cloud features, which are fed through point bird and then linearly projected. But one problem of point bird is that it needs normalized object point cloud, so the shape information is lost. So the object size information is lost. So that object size information has to be embedded in a separate token here. And OS token represents here the object size token here. And for this language part, it takes the user instruction And then together they go through the LLM, and the LLM outputs the OM and R token. And that is used by VQVAE to generate the hand pose, the hand grasp. Now, a problem they faced is that to do their task, there is no similar data set with that has the language annotation on high level, low level. So they had to make their own data set. They named it cat grasp data set, which they made out of Oking data set. For low level annotation, they refer to the contact relationship between each finger and various parts of the object. And then they use the CAD models in the Oking and the object part segmentation and hand vertices to get the contact relationship. According to the grasp taxonomy of the grasp type, and intent from the low-level annotations can then be deduced. Utilizing this information, the context states is calculated when the distance between the hand vertices and the object's part segmentation points is less than a threshold of 3 millimeters. For instance, if the thumb and index finger are in contact with the screw, it is inferred that the grasp type is a pinch, and the intent is to screw or unscrew. High-level annotations. Based on low-level annotation, based on low-level contact information, given this information, the finger and the object part contact, GPT-4 is employed to infer the grasping intent. For example, if all fingers are grasping the handle of a mug, GPT-4 can deduce that it is a firm grasp with possible intents such as make a toast or avoid hot beverage. And another way it makes the high-level annotation is based on images or rendered views, where GPT-4 is used to infer high-level information such as manipulation intent and grasp force. For conversation and annotation as well, they use GPT-4. With low-level and high-level annotations, conversations using the GPT-4 model is constructed. GPT-4 is asked to generate various conversational templates from different perspectives, including detailed hand object contact information, manipulation intent, grasp force, and type. Statistically, the dataset includes approximately 1.8 thousand object models from Oking, about 50,000 hand object grasp pairs. For the experiment part, for evaluation, as evaluation metric, they use for the physical plausibility section, they use mean MPVP, penetration depth, solid intersection volume, and simulation displacement. Simulation displacement is objects' center displacement under steady hand condition and gravity in the pipe-led simulator, which measures this is done to measure the grasp stability. And then metrics to evaluate semantic consistency. They use GPT-4 assisted evaluation, which first renders the hand-object interaction, where the hand-object interaction is rendered, then GPT-4V is used to score the semantic consistency of the grasp images based on input captions. Scores range from 0 to 100, with higher scores indicating better consistency. And then they use PFID and perceptual score. Perceptual score assesses the naturalness of the grasps and semantic consistency, with 5 volunteers rating the generated grasps on a 5-point Likert scale. The final score is the mean Likert score. Implementation details. PointBird is employed as the point cloud feature extractor in the VQV encoder for both hand and object vertices. For the MLLM, Llama structure is used as the backbone, fine-tuning based on the Vicuna 7 billion checkpoint. To extract object feature, FO, VQVA is reused from PointBird and its parameters frozen. LoRa module is configured with rank setting of R equals 64, resulting in approximately 6% parameter being fine-tuned. MLLM is trained over 20 POCs on 4 A100 GPUs with 80 GB of memory each. And for experiment results, they compare with GrabNet and Jiang et al.'s work. GrabNet uses refinement naturally, but they tried without refinement, and TTA here refers to test time adaptation, which is originally used by Jiang et al. So for here, hours without fine-tuned token refers to not using the refinement token, and with test time and with W with TTA refers to their setting with test time adaptation similar to Jiang et al.'s. And for most of the metrics, well, for NTP, PD, and SIV, the top scoring ones are from their model, some variant of their model. For SD mean and SD standard deviation, the best one is GrabNet for TTA for SD mean, and Jiang et al. With TTA for SD standard deviation. To explore whether their discrete representation method can encode semantic information, they conduct a control-level generation task. For GrabNet, the conditional VAE-based method, the sampling vector is fixed to z equals 0, enforcing the model to generate similar grasps. For their model, they assign the same constant value to the tokens. So they set z equals 0 for the GrabNet, and for PQ, for their model, they set OM token to constant, and they use for object they use mugs of different types, and while for GrabNet conditional VAE, the grasps change to vary a lot depending on the mug type, but in their model, since it's a mug, even though the mug type varies, the grasp is the same, indicating that their model has better semantic understanding of the object features. And for the language evaluation, there is no other model to compare with, so they changed the official BERT. The official BERT model is fine-tuned to embed the language description in conjunction with the object feature. Subsequently, 3 distinct classification heads are deployed to predict the tokens, the OM and R tokens. This modified BERT is trained with CapGrasp dataset following the same settings in SemGrasp. And their setup, the SemGrasp came out to be top in all the metrics except for SDSTD. And these are the qualitative results. The grasps on the object and the prompts they use. And here are some failure cases. Now for ablation study, 1 token here represents just using 1 token instead of 3 tokens. And OM here indicates no refinement token. And for this one, they use 2 refinement tokens. And this one, 3 refinement tokens. And here, instead of a hierarchical VQVAE, they used a single VQVAE. And without semantic implies no semantic meaning assignment to the tokens generated from the hierarchical VQVAEs. So no OMNR assignment. And theirs came out to be the top. The full setup came out to be the top in all the metrics. And for VQVAE settings, they changed the codebook entries. Their codebook size was K equals 512. Less or more are both worse. They either overfit or underfit. And dimension for them is 256. And even in this case, less or more is worse than their setup. And this is ablation study of MLM-based grasp generation. This is with just base llama, and this is without the object size token. This is without two-stage training. This is with LoRa equals 16 instead of 64, and this is with LoRa rank equals 128 instead of 64. And SemGrasp comes out to be the best compared to all the cases. Thank you for listening. That's it for me.